Assalamu alaikum. We are going to start one of the toughest and lengthiest course of mechanical engineering department, which is heat and mass transfer. The course code is ME315. These are the recommended books of heat and mass transfer, Fundamental of Heat and Mass Transfer by Cropra and David. Seventh edition will be followed, and this edition is easily available from internet. You can just write Fundamental of Heat and Mass Transfer 7th edition. You can easily download this book. Another book which will be used is Heat and Mass Transfer by Eunice Sangel 5th edition. This book is also available on internet. The first book, Fundamental of Heat and Mass Transfer by Incropra and David, will be considered as our textbook. Now moving toward the CLOs of this course, the first CLO is apply expression of heat transfer modes on various thermal system. This CLO is mapped with PLO1. The second CLO is apply convection and mass transfer analogies for determining related parameter and coefficient. This CLO is mapped with PLO2. The third one is the design of heat exchangers using standard practices. This is mapped with PLO3. We have CLO4 related to our lab, which will be discussed when you will conduct the experiments. So these are the three CLOs of our theory. You can write this these CLOs in your textbook, and your assessment will be based on these CLOs. Now, our first lecture is related to the introduction. In this lecture, we will discuss what is heat transfer, what are the different modes of heat transfer, what causes the heat to transfer. So, the first question which comes in our mind after reading the title of this course is that what is heat? What basically heat? We use this word heat in our daily life, but do we know the meaning of heat? So, heat or heat transfer is a thermal energy in transit due to spatial temperature difference. This is the simple definition of heat transfer, that heat is a thermal energy which transmit due to temperature difference. Heat is simply energy which is flow due to temperature difference. Whenever there is a temperature difference exists between two bodies, then there will be a flow of energy between them, and that energy is known as heat. For example, we have two blocks, block A and block B, as shown in figure. Block A has higher temperature than block B. There is a temperature difference exists because block A has higher temperature and than the block B. So there is a temperature difference exists between block A and block B. So there will be a flow of energy between block A and block B due to their temperature difference. That flow of energy is known as heat. And remember, heat always flow from higher temperature to the lower temperature. It means that block A has higher energy than block B. Block A will lose energy and block B will gain energy. This energy transfer or heat transfer will continue until the temperature of both the blocks become identical. It means when the temperature of block A becomes equal to the temperature of block B, then the heat transfer between these blocks will stop. No more heat transfer between these blocks. So heat is the energy flows due to temperature difference, and heat always flow from higher temperature to the lower temperature, and heat flow will continue until the temperature of both the bodies becomes identical. Clear? I think it's clear up to you about the heat, that what is heat. This is the basic of heat. Now the first question which comes in our mind is that what is the difference between thermodynamics and heat transfer. We have studied thermodynamics, which is also related to heat. Now we are studying heat transfer. So what is the difference between thermodynamics and heat transfer? Thermodynamics. In thermodynamics, we basically deals with the amount of energy in form of heat or work during the process and only consider the end states in equilibrium. In thermodynamics, we convert heat into work and we only consider the end states in equilibrium. Thermodynamics gives no information about how long it will take to reach the final state in equilibrium, while heat transfer deals with the rate of energy transfer. Thus, it gives the idea of how long a heat transfer will occur. Heat transfer tells us about how much heat transfers and how long will it take to reach the equilibrium state. In short, heat can only transfer when there is a temperature gradient exists in the body, which is indication of a non-equilibrium phenomenon. So thermodynamics deals with the end state and it gives no information about how long will it take to reach the final state, while heat transfer deals with the rate of energy transfer and it gives the idea of how long a heat transfer will occur. I think this will clear you about the difference between thermodynamics and heat transfer. That is why we are saying this course heat transfer, not thermodynamics 2. This is heat transfer. This is not thermodynamics 2 or advanced thermodynamics. These are separate terms and heat transfer is separate terms. So always remember that thermodynamics is something different and heat transfer is something different. And this slide gives you about the complete information. This slide gives you the complete difference between thermodynamics and heat transfer. What are the different modes of heat transfer? I think you have familiar with the different modes of heat transfer. You have studied in your intermediate the different modes of heat transfer, and the different modes of heat transfer are conduction, convection, and radiation. All of these heat transfer will be studied in detail in this course. But now we are moving towards conduction, basics of conduction. So in order to understand what is conduction, we will watch this video.
Flow of heat. You will learn about flow of heat through conduction. Matter is made up of atoms and molecules. They are constantly in motion producing heat or thermal energy. Heat transfers from one place to another in three different ways: conduction, convection, and radiation. Conduction. The heat transfer by direct contact of particles of the matter is called conduction. The heat transfers from higher temperature to the lower temperature by migration of atoms in a molecule. Conduction activity. Light a candle and heat one end of a metal wire. You will notice that after a few minutes, the wire gets warm and the temperature rises to an extent where you cannot hold the wire anymore. This is because the heat travels through the wire. The heat passes through it due to vibration of atoms within the wire. Good conductor of heat. Conduction of heat depends on the material. A good conductor of heat allows heat to flow through it because of its free electrons. Metals like copper, iron, and aluminium, etc., are good conductors of heat. Bad conductor of heat. Substances that do not carry heat are called bad conductors of heat or insulators. There is no transfer of heat as atoms might be either too close to have any space for vibration or farther away from each other to allow any transfer of heat to neighboring atoms. For example, wool, plastic, and glass are bad conductors of heat. Conductor of heat activity. Place a metal sauce pan with a plastic handle on a burner. Pour some water and let it heat. The water starts to boil, but when you place your hand on the handle, you will notice that it is cold even though the saucepan is very hot. This is because the metal, being a good conductor of heat, transfers heat all over the pan, and as the handle is made of plastic, it lacks free electrons for the heat to flow through it, keeping the handle cold all the while. In this session, we have learned the following. Heat is produced due to vibrations of atoms in matter. Conduction is migration of atoms from higher temperature to a lower temperature. A substance is a good conductor when there are lots of free electrons that can carry the heat. A bad conductor has atoms that are either too close to vibrate or too far to transfer any heat.
So, in this video, we have learned that conduction occurs due to the transfer of energy from more energetic particle to the less energetic particle of a substance due to interaction between these particles. Consider we have a gas confined in a block as shown in this figure. The upper side of the block is at a temperature T1 and the lower side of the block is at a temperature T2. Side that T1 is greater than T2. The upper side of the block has higher temperature than the lower side of the block. The particles of a gas near the upper side of the block has more energy than the particle at the bottom. These particle will move from higher side to the lower side, and the particle near the bottom side will move towards the upside because they have lower energy. So heat will transfer from higher temperature to the lower temperature. So heat will transfer from upper side to the lower side because upper side is a higher temperature than the lower side. So conduction is basically a heat transfer from more energetic particle to the less energetic particle. There are different rate equation which quantify the amount of heat. For conduction, the rate equation is given by Fourier's law, and the equation of Fourier's law is simply Qx double dash is equal to minus K dt over dx. Qx double dash is the heat flux rate in the x direction per unit area perpendicular to the direction of heat. What is heat flux? We will discuss in next slide. Here K is the transport property and it is separate for every material. It is a constant for each and every material, and this K is known as thermal conductivity. The thermal conductivity of each and every material is different. For example, the thermal conductivity of copper is different from that of iron, from that of aluminium, from that of wood or plastic, and the material with higher thermal conductivity are considered to be conductors, while the material having low thermal conductivity are considered to be insulators. Dt over dx is the temperature gradient in the x direction. Since heat is transferring in x direction, so temperature gradient in x direction, dt over dx. Now, what is the direction of heat transfer? As we studied that heat always transfer from higher temperature to the lower temperature. Consider we have a cube. The face of cube, the face ABCD of cube is at temperature T1 and the face EFGH of cube is at temperature T2, such that T1 is greater than T2. So heat will flow from higher temperature to the lower temperature. This green arrow shows the direction of the heat transfer, that in this direction heat will flow because phase ABCD is at higher temperature than phase EFGH. Heat always flow from higher temperature to the lower temperature, so heat will flow from ABCD to EFGH. Now we have studied the term heat flux in the previous slide. Now what is heat flux? This is the heat transfer. This green arrow shows the heat transfer, and this is the perpendicular area. The area ABCD or EFGH is the area perpendicular to the direction of heat transfer. So heat flux will be the heat transfer divided by the area ABCD. Heat flux will be the heat transfer per unit area perpendicular to the direction of heat. The area perpendicular to the direction of heat is the phase ABCD or EFGH. So heat flux is simply the heat transfer per unit perpendicular area. And remember, heat always flow from higher temperature to the lower temperature. Now we are going to solve one solved example of our book in Cropra and David. This is example 1-1 that we have. This is example. The wall of an industrial furnace is constructed from 0.15 meter thick fire clay brick having a thermal conductivity of 1.7 watt per meter Kelvin. Measurements made during steady state operation reveal temperature of 1400 and 1150 Kelvin at the inner and outer surfaces respectively. What is the rate of heat loss through a wall that is 0.5 meter by 1.2 meter on a side? We have a wall of industrial furnace having thickness of 0.15 meter and it is made up of fire clay brick. The thermal conductivity of a fire clay brick is 1.7 watt per meter Kelvin. Measurement made during a steady state operation, and it is found that the temperature at the inner side of the fire of the furnace is 1400 Kelvin, while the outer side of the furnace is at a temperature of 1150 Kelvin. Now we are going to find the heat loss through a wall, which is 0.5 by 1.2 meter on a side. This is the schematic. This is the fire clay wall, fire clay brick wall. It has a thickness of 0.15 meter and the width of the wall is 1.2 meter and height is 0.5 meter. The temperature at the inner side of the wall, this is the inner side of the wall, which is shown here, that it is at a temperature of 1400 Kelvin, and the outer side of the wall, which is this wall, it is at a temperature of 1150. Heat will transfer from higher temperature to the lower temperature. Heat will flow in this direction, which is shown here by this arrow QX. We have thickness of the wall 0.15 meter. We have thermal conductivity of the material around 1.7 watt per meter Kelvin. The temperature at the inner side, we have mentioned T2. It is up to you that either you are taking inner side T1 or outer side T2. It's up to you. It doesn't matter. Inner side temperature is 1400 Kelvin, while outer side temperature is 1150 Kelvin. Area through which the heat transfer occurs is 0.5 meter by 1.2 meter. Using Fourier's law of heat transfer, which is Q is equals to minus K A delta T over delta X. In previous slide, we have learned Qx double dash is equals to minus K dt over dx. Dt over dx is replaced by delta T over delta X. If delta T over delta X tends if delta X tends to 0, then this will convert into dt over dx. And we have learned Qx double dash, which was heat flux, and heat flux is the heat transfer per unit area. So if we multiply the heat flux by area perpendicular, so we will find the heat transfer. So according to Fourier's law, heat transfer is Q is equals to minus Ka delta T over delta X. After substituting the values of Ka delta T over delta X in equation of Fourier's law, we have found that heat transfer of heat transfer of will occur from higher temperature to lower temperature, and heat transfer comes out to be minus 1700 watt. Here minus sign is indicating that heat is transferring from higher temperature to the lower temperature. This minus sign shows that heat transfer will occur from higher temperature to the lower temperature. So Q is equal to minus 1700 watt. This is the simple numerical which gives the idea of conduction. Now we are moving towards the another mode of heat transfer, which is convection.
Heat can transfer through them fairly easily, and the way it does this is by convection. Convection occurs only in fluids. Now by fluid, we just mean a liquid or a gas, something that can flow. And the way it happens is always the same. So let's look at the gas particles in this room. They all have roughly the same energy, which we can see because they're all moving about the same speed. So let's put a fire in the room. Okay, now the particles by the fire start to gain energy from it, and they start to move faster. And because they're moving faster, they spread out. So that bit of fluid becomes less dense. And because it's less dense, it rises. Now, when those particles rise, they can't leave nothing behind. So the cooler air or fluid moves in to replace them. But now this cooler fluid is by the fire. So these particles start to gain energy. And this bit of fluid then becomes less dense than the fluid above it. And it rises, pushing the other particles back round. These are now back by the fire. So guess what? They're going to gain energy. They're going to get even hotter. They're going to become even less dense. They're then going to rise. This is going to happen over and over again, forming a convection current. And that is how heat transfers through fluids, liquids and gases. So, what are the key points here? Well, the key points are that in convection, fluid near the heat source gains energy, becomes less dense and rises, being replaced by cooler fluid, which then in turn gains energy, becomes less dense and rises, forming a convection current, which then heats the fluid completely. Heat can transfer through them.
As we have learned from the video that convection heat transfer occurs between a fluid in motion and a bounding surface when the two are at different temperature. Consider we have cold air passing through these blocks which are at higher temperature than the air. When the air particle come in contact with these hot blocks, their temperature, the particle near these blocks will gain energy, due to which their temperature increases. As the temperature of these particles increases, their density will decrease, due to which they will move upward, and the particle which are at upside will have lower temperature, they have higher density, so they will move downward. those particles will gain energy, their temperature will increase, due to which their density will decrease. So there will be a setup of convection current, as we have seen in the video that there is a setup of convection current. When the air particle come in contact with these blocks, they will gain energy, due to which their temperature increases. As the temperature of the air particle increases, their density will decrease, due to which they will move upward, and the particle which are at upside will move downward, because their density is higher than the hot particles. The cold particle will come downward. Those cold particles will then gain energy, and their temperature will increase, due to which their density decreases. Those cold particles will become hot, and those particles will move upward. So there will be a setup of convection current. So remember, convection heat transfer occurs when there is a fluid in motion. So convection heat transfer is basically a conduction plus bulk fluid motion. Whenever there is a fluid in motion, then the heat transfer will be convection. The rate equation which quantify the convection heat transfer is given by Newton's law of cooling, and it states that Qx double dash is equal to HTS minus T infinity. Qx double dash is the heat flux, as we have learned in conduction. Nothing different in convective heat flux and conductive heat flux. Both are heat flux and both are the heat transfer per unit perpendicular area. Ts is the temperature of the bounding surface. For example, in this figure, Ts is the temperature of these blocks. T infinity is the free air stream temperature. T infinity is the fluid temperature, due to which convection heat transfer occur. T infinity, remember, is the fluid temperature, and Ts is the surface temperature. Here H is the parameter known as convective heat transfer coefficient, and it is different for each and every case. It is not a constant property, it is different for each and every case. For example, it is different in case of turbulent air, and it is different in case of laminar flow of air. We will discuss how this H is determined in detail when we study convection in detail. Now we are moving towards the third mode of heat transfer, which is radiation, and for radiation we will again watch a video.
So far, we've looked at conduction and convection, and both of these methods need particles to transfer heat. But heat manages to get to us from the sun, and there's definitely no particles in space. It's a vacuum. So, how does the heat from the sun get to us? Well, it travels as radiation, infrared radiation, or heat radiation to be precise. So, let's look more at this process of heat transfer of radiation. We actually find that different colours are better at emitting heat than others. Now, all hot objects emit heat radiation, and this is a physics term of hot. What it essentially means is any object above 0 degrees Kelvin, or minus 273 degrees Celsius. That's what us physicists mean by hot. So anything above that emits heat. However, it will also be absorbing heat radiation. And it's only if it's hotter than surroundings that it's actually going to be emitting heat overall. So, let's add some boiling water to this cube to make it hotter than the surroundings. And let's see what happens. First, let's look at the shiny silvery side. We can see that's really rubbish at emitting radiation. There's hardly any waves coming out of there at all. We then turn to the white shiny side. You see that's only marginally better, still pretty rubbish at emitting radiation. The matte white side, slightly better, but still pretty rubbish. Let's go round to the shiny black side, and we see all of a sudden that is emitting a fair bit of heat now. But now if we turn around again and we see the matte black side, we can see that is going like crazy. That is emitting loads of heat radiation. You can see from this that matte black is the best colour at emitting heat radiation. So, what colour is going to be best at absorbing heat radiation? We've seen that matte black is definitely the best emitter, but what colour is going to be the best absorber? So there's a really easy experiment for this. We have a nice heat source in this form of a fire, and we can stick, using just some wax, 2 marbles onto a couple of plates. One plate with a shiny surface, and one plate with a matte black surface. So, whichever surface absorbs the most heat radiation is going to melt the wax the fastest, and therefore the marble will drop quickest. So which one do you think it will be? Well, let's look and see what happens. Well, first off, I can notice that the shiny silvery surface is reflecting away all of the radiation. The matte black surface seems to be absorbing all that radiation. So I'm going on, there we go. The matte black fell off way in advance of the shiny silvery one. The shiny silvery one's still pretty stuck on there. And we can see why. It's because matte black is absorbing all that radiation, shiny silvery is reflecting it. So what's the key information for us to have here? Well, when heat needs to transfer across a vacuum, the only way it can do it is by radiation. We've also seen that matte black is the best absorber and emitter of radiation. And that's why if we want something to heat up really, really quickly, or something to cool down really, really quickly, we colour it matte black. We also saw that shiny silvery surfaces were the worst at both absorbing and emitting radiation, and that's why if we want something to stay hot, or if we want something to stay cold, we use a shiny silvery surface.
In both conduction and convection, we have seen that there is a requirement of material medium. Conduction occurs due to transfer of energy from higher energetic particle to the lower energetic particle of a substance. It means there is a requirement of material medium. Convection occurs between the bounded surface and the fluid in motion. It means that there is a requirement of fluid in convection. Without fluid motion, convection doesn't occur. So both conduction and convection requires material medium. While we know that we receive tremendous amount of heat at earth from the surface from sun, and we know that there is no material medium between earth and sun, so there is a third mode of heat transfer which occurs without the presence of any material medium, and that mode of heat transfer is known as radiation. Now what is radiation? Thermal energy Thermal radiation is energy emitted by matter that is at a non-zero temperature. Every body which is at non-zero temperature emits radiation in the form of electromagnetic waves or photon. Every real body emits some radiation or thermal radiation, which is energy, and that energy is transported by electromagnetic waves or protons. In short, every real body emits electromagnetic waves, and that electromagnetic waves are responsible for the heat transfer, which is known as radiation. I am saying every real body which is at non-zero temperature. Every real body means that I am emitting radiation, you are emitting radiation, the furniture around us is emitting radiation, the laptop, mobile, every real body, even gases, liquids emitting radiation because they are at non-zero temperature, and these radiation does not require any material medium to travel. That's why thermal radiation, or the simply radiation, is the heat transfer mode occurs without the requirement of material medium. The heat we receive from sun at earth is due to radiation. The amount of emissive power, or the amount of radiation emitted by a body, is given by Stefan Boltzmann constant, which is EB is equals to sigma Ts power 4. This is the emissive power of a black body. Black body does not mean to be black in color. We will discuss in detail what is black body when we study radiation in detail. This is the EB is equals to sigma Ts power 4 is the black body radiative power, or black body emissive power. But real body emit radiation less than the black body, and the emissive power of the real body is given by EB is equals to epsilon sigma Ts power 4, where epsilon is known as emissivity of that body. Remember, real body emit radiation less than the black body at the same temperature. This is the amount of emissive power which emits by a black body, and this is the amount of emissive power emitted by a real body. Now consider we have a block which is a temperature of Ts, and its surrounding is at a temperature T surrounding, such that the temperature of block is higher than the temperature of surrounding. So the radiation heat transfer will occur from the block to the surrounding. The amount of radiative heat transfer is given by Q is equals to epsilon A sigma Ts power 4 minus T surrounding power 4. Here epsilon is the emissivity, A is the area perpendicular to the heat transfer, sigma is the Stefan Boltzmann constant, and its value is fixed, which is 5.67 exponent minus 8 watt per meter square Kelvin power 4. Remember one thing, that this temperature is absolute temperature. It means that when we are going to solve radiative heat transfer question, then we should put the value of temperature in Kelvin scale. For conduction and convection, it's our choice that either we put the value in degree centigrade or in Kelvin, but for radiation we have to put the value of temperature in Kelvin scale. If we put the value of temperature in degree centigrade rather than Kelvin, then our result will be full of error. So in order to eliminate those error, we should put the value of temperature in Kelvin scale. But for conduction and convection, we can put the value of temperature either in degree centigrade or in Kelvin. But for radiation, it is mandatory to put the value in Kelvin scale. With that, we have done with our lecture number 1. In lecture number 2, we will do some numerical related to the conduction, convection and radiation that we have learned in lecture 1. Lecture 2 will be consist of numerical, and those numerical will be related to lecture number 1.